This is Linked Data Engineering, lecture number 3, Linked Data Vocabularies and Ontologies. In this part of the lecture, we will learn a little bit more about the web ontology language OWL. As we have already stated, we are right now in the semantic web technology layer cake in the modeling layer, where also RDFS and other modeling languages are located. So now it's the web ontology language. Let's continue with the definition of classes in OWL. Besides defining something to be a class, we can define complex classes. For example, we can define classes as being a set of specified individuals. These are so-called nominals. I simply define the class by stating which individuals belong to this class. So here, for example, look at the following example. We have novels, which are a class. We have Animal Farm, which is a novel, and 1984, which is also a novel. Now I define a new class, which I call novels in store. And I say this class is constituted of the following two individuals of Animal Farm and 1984. And the keyword I use for that is OWL one-off. So this is a special keyword of the OWL vocabulary, which is a property and which states that the class which is related to exactly that property contains the collection of things which are mentioned as an object. So here Animal Farm and 1984. And you can of course continue this collection of things. No problem. So if you define a class as a collection or a set of individuals, these are so-called nominals. This is one way to define complex classes. Let's look at other ways. What you have, for example, you have the possibility to combine already existing basic or complex classes. So for example, you can combine two classes via an intersection, so the intersection of two classes. Or you can also use the union of two classes. So this is like in set theory. And you can also negate a class and can define the class's complement of another class. So with these logical constructors, you are able to give complex class definitions and complex class descriptions. Let's take a look at a few examples. First, let's start with an example. How do I define a class as being the intersection of other classes? Here in our example, we have books, which are a class, and we have things in store, which are a class. And now I define books in store, which is the class that consists of the intersection of the things that I have in store and the books. Sorry, quite simple. So I define books in store as being a class, and then I simply say, okay, I assign to this class another property, which is OWL intersection of, and then I write simply the collection of things which are here used in this intersection, which are the two classes, things in store and book. And of course, I could also extend this collection and could make further intersections. And in the same way I do an intersection, I can also do a union. Let's have a look at the following example. There I do a more complex definition of a fact simply because I declare one class to be equivalent to a complex class expression. So what I do here, just take the first look here on the gray description logic statements. I declare a book to be the union of novel, poetry, and non-fiction. Now let's have a look at the same thing described in OWL, in the web ontology language. I define book to be a class, and I say this class is equivalent to the following expression. So the following expression now in square brackets. So this points in the related graph to a blank node, and this blank node then is bound to a OWL union of, which says now this is a union of several classes, which are then simply in parentheses named or enumerated in a collection you see here as novel, poetry, and fiction. So this would be the OWL description of a union of classes. And I say book is a class which is equivalent to exactly this union. Okay, next example uses the same way to describe a complex class as the subclass of another class. So I say here book is a class, and this is a subclass of, so I can use RDF as subclass, and then comes my compound, which says I take here the complement of a class. I say book is a subclass of non-writer, of the complement of writer. The complement of writer is everything which is not a writer. And of course, a book is not a writer, so therefore this expression is semantically equivalent to the assertion that book is a disjoint class with writer. So book is disjoint from writer or with writer. This is the same or two different ways to express the same kind of knowledge. So in this way, you would use the complement of a class to define a new class, a more complex class. Likewise, we have described classes. We can now use property restrictions to define also complex classes. So we have several keywords which are introduced here and which I will explain in detail to you in the following slides. First, we have restrictions on values of properties with which I can define classes. So for example, I could define a class that all members of the class, they have a specific property or attribute, and this property must have a specific value. This is a complex class description based on property restrictions. So let's have a look how this works. Of course, first we look at an example. First again, look at the description logic expression. This is given here in light gray below the gray box with the OWL language. What I want to define here is something which is called Orwell's books. And Orwell's books should be a subclass of everything which has the author George Orwell. Seems logical. Is given here, for example, I say here Orwell's books is a subclass of, author then is the property, and then I do a restriction on the range. So this is a range restriction, and I say the range must be of the value George Orwell. How does this work? In OWL, so we define Orwell's books as a class, and then we say this class is a subclass of, and then we define a new construct given here in square brackets and say, okay, this construct is a so-called OWL restriction. The restriction is on a specific property. So we say we have another keyword which is OWL on property, which says now the property on the property author. We give a restriction, and the restriction is of the type value restriction. So we say this property must have a specific value, and the value here is given as George Orwell. These value restrictions, of course, are also working with data type restrictions, data type properties. So if author would not be an object property but a data type property, then OWL has value would also have a literal as object here, in which you can restrict this thing. So what you do here, you describe the class Orwell's books via a fixed value assignment or constant assignment of the individual George Orwell to the property author. And this defines Orwell's books. Another example, what I can do with a property restriction, it's a so-called strict binding. What I do here is I want to bind all possible individuals in the range of a property to a specific class. So for example, I define here poetry. Just look first at the gray description logic expression. I define here poetry as being a subclass of something which is authored only by a poet. So all members of the class must have the property author, and the range then must be, the individual which is connected to must be of the class poet. Only then it is poetry. So poetry is always written by an author. This is the way how you read that. Just have a look at the corresponding OWL property restriction. So we define property as being an OWL class. And then we say this is a subclass of a compound, given here in square brackets, of a restriction. So this is an OWL restriction, again on a property, the same property as before, again on the property author. And now there is a new keyword. I say all values from, which restricts all values of that used property author to a specific class, namely to the class poet. So poetry must be written by poets and nobody else. This is the OWL all values from restriction, and this is a strict binding. Simply it fixes all the instances of a specific class C as a allowed range of a property P as a strict binding, as you see then here. So all individuals here are bound to a specific class in the range of that property. And therefore I define a new class with that. So if I have a restriction which confirms to or fixes all individuals in that range, I can also think of of a restriction which simply says, oh, there must exist at least one thing or one binding here, but of course there can also be other bindings in that class. And this you do, for example, here. So this is an existential restriction, or also called loose binding on that property. For example, if I want to define a reader as being a subclass of somebody who reads, for example, books besides other things, then I can define it in the following way, that I say reader is an OWL class, and this is a subclass of a compound which is a restriction, and the restriction this time is on the property reads, and now I have a new keyword which says OWL some values from, which binds now the range of reads to something which is a book. But the interesting thing is a reader can also be somebody who reads besides books other things. And this would be not possible in our strict binding that we had before. The strict binding, there is only one class allowed that is fixed here in this property restriction. In a loose restriction, a reader can read books, but can read also other things. He does not have to, it can only be books, but it can be. So, some values from here describes that there must exist an individual for this property P and fixes its range to a class in the sense of a loose binding. So this is an existential property restriction. Don't worry, we will have this in the exercises and you will certainly learn that, and you will value the use to define these more complex classes. So besides the restriction exactly on that property value, we also have the possibility to restrict the cardinality. How often is this property used for an individual being member in a class? So for example, if you want to define something like a tetralogy, which consists of 4 volumes or 4 books, you can do it in the following way, that you say a tetralogy is an OWL class, which is a subclass of a compound, which is a restriction, this time on the property has volumes, and you say the cardinality of it via the OWL keyword, OWL cardinality, must be exactly 4. This is a tetralogy. It should not be 3, it should not be 5. In this class are only members which have 4 times the property has volumes, exactly 4 times. So this is a tetralogy. So OWL cardinality, this keyword restricts to an exact number. Sometimes you only want to give upper or lower bounds. This is also possible. Therefore, you have the OWL keywords min cardinality and max cardinality as upper and lower bound. So this is for OWL cardinality restrictions. Now we have learned a lot about defining complex classes in OWL. What follows next is the definition of properties and also property restrictions. So next lecture will be OWL and beyond.